Hi, I stand before you today to present a topic that combines cutting-edge technology and the mining industry, titled Digital Twin Enabled Monitoring of Mining Haul Tracks with Expert System Integration, a case study in an experimental open-pit mine. It's Nabil Bazi, a research and development engineer and PhD student at the Green Tech Institute of Mohammed VI Polytechnic University of Bengurir, Morocco. In this presentation, we will explore how digital twin technology, coupled with expert system integration, has been employed in monitoring mining haul tracks within an experimental open-pit mine. We will delve into the challenges faced by the industry, the objectives of the study, and the methodologies employed to achieve our goal. Throughout this presentation, we will showcase the state-of-the-art, including the digital twin technology, monitoring system, and mining haulage, the deployed materials and the followed methods, the design and results, and at the end, throughout the discussion section, we will highlight the key findings, lessons learned, and the potential application for the wider mining sector. In the mining industry, the use of digital transformation has become increasingly important to improve the productivity, efficiency, and availability of machinery and equipment. The implementation of digital twin technology has shown great potential in tackling issues related to maintenance, production, and safety in the industry. This paper presents a case study on the development of a digital twin-enabled monitoring system for the mining haul tracks with expert system integration. In many mining operations, material movement, also known as haulage, is a major bottleneck. As haulage impacts the operation's productivity, efficiency, cost, and sustainability, it is important to make the best possible use of haul tracks movement, especially in terms of poorly timed trips to the supply station. For that issue, the digitalization is representing a big opportunity to handle the challenge. Throughout the use of the monitoring tools using digital twin technology to optimize one of the major activities in the mining industry, namely the mining haulage. The digital twin technology has a wide range of applications and advantages. The information flow across all business operations is linked by digitalization, which is the foundation that enables you to adapt swiftly to changing business situations. An Industry 4.0 tool called the Digital Twin method will link and optimize your company, allowing it to operate to its fullest potential. Digital twin technology as a promising tool for improving the performance of physical systems has been applied in many areas, including manufacturing, construction, healthcare, and transportation. This technology enables to create a virtual replica of a physical system, allowing for real-time monitoring and analysis of the system's behavior. Monitoring systems are a key component of digital twin technology as they collect data from physical system and assets and feed it to the digital twin for analysis. In recent years, there have been significant advancements in monitoring systems related to digital twin technology. OEE, or overall equipment effectiveness, is widely used as a performance indicator in manufacturing industries, and also it can serve as a percept and indicator of digital twin to recognize the real-time situations in a manufacturing system. OEE is considered most suitable for simultaneous and automatic manufacturing processes and originates from the highly automated semiconductor industry. Availability corresponds to the ratio of planned production time with downtime to the planned production. Time, performance, efficiency is the ideal cycle time multiplied to the number of products produced divided by the actual runtime. Quality rate is the ratio between accepted products and the total quantity of products produced. Mining haulage activity is an essential component of the mining process, and its importance cannot be overstated. The efficient movement of materials and equipment through a mining operation is critical to its success, and optimizing haul track movement is key to achieving productivity, efficiency, and sustainability goals. As the mining industry continues to evolve, finding innovative solutions to improve mining haulage practices will be critical to meeting the industry's economic and environmental challenges. So, according to our presentation, the third section is materials and methods. In this section, we will talk about the data model. The data model is depicting the accordance with a methodology that involved four main steps: data inventory, programmable logical controller data classification, data modeling using the Mery's conceptual modeling approach, and structured database design. Starting by the first step, which is the data inventory, involved sorting the PLC data types and addresses, which allowed for a better understanding of the data to be modeled. This was done by categorizing the various types of data as well as mapping their addresses. Secondly, the PLC data classification involved categorizing the data into three groups: outputs, indicators, and instructions. This step enabled the differentiation between the various types of variables based on their respective roles in the system. Now, with the data modeling, using the Mery's conceptual modeling approach that involved defining the entities, relationships, and attributes that were relevant to the modeling of data. The Mery's methodology was chosen for its ability to effectively model complex systems and relationships in order to design the main database. Now, with structured database step, which involved organizing and structuring the data in a way that facilitated easy access and retrieval. This step was important for ensuring that the data was organized in a logical and intuitive manner, which would allow for efficient querying and analysis. Now, we will talk about the state machine diagram of the system. The state machine diagram presented here in the figure is revealing 6 distinct states, namely data acquisition, SCADA monitoring, data logging, processing, analytics and trends, and finally decision making. The 6 states are depicted as nodes, and the arrows connecting them indicate the conditions that enable the transition between states. When a state is activated, specific actions take place, ensuring the system's operation. In the initial state of the system, the process of data acquisition is initiated, wherein the data from the mining haul track is collected using a PLC installed on the track. The collected data is stored in the multi-controller server data, which utilizes the OPC factory server OFS, establishes a physical connection via cable Ethernet Cat6a supporting the Modbus TCP protocol and enables the connection with the SCADA monitoring system. The data is then monitored in real time using the SCADA monitoring system. Following the real-time monitoring of data, 2 triggers are implemented to enable the logging of every change in the variables in accordance with a predefined logging policy. Trigger number 1 is designed to monitor all digital variables, and it is activated for every change in the state of any discrete variable. Trigger number 2, on the other hand, is responsible for monitoring analog variables by setting a sampling period of 1 second or at every change in the discrete variables. This approach ensures that all changes in the data are accurately captured and logged for further processing and analysis. Upon entering the processing system state, the logged data undergoes the statistical process control algorithm. The aim of this process is to prepare the data for the next state, which involves analytics and trends. To achieve this, the statistical process control algorithm employs the Shewhart control chart, a widely used statistical tool that facilitates the analysis of the overall system and provides visual representation of any anomalies or defects. In the final stage of the presented system, the outputs of the analytics and trends state are visualized using a Shewhart control chart, and the analytics are prepared. At this point, a human expert agent is called upon to deploy their process knowledge to validate the detected anomalies' origin and propose appropriate instructions to address these situations. Now, this slide is about the deployed algorithm. The SPC algorithm, or statistical process control, is a common method for monitoring and analyzing data collected from assets. Its control charts are a widely used approach which involves plotting data over time and comparing it to predetermined control limits. These control limits are derived from the data and are utilized to identify any unusual patterns or deviations in the data that may indicate a problem with the track's performance or safety. So as we see in the last state of the state machine diagram, we have used the expert system. This expert system was integrated into the digital twin of the mine and haul track to enhance their performance monitoring capabilities. The expert system utilized in our study is a type of artificial intelligence system that emulates the decision-making abilities of a human expert in a particular domain. It is designed to process and analyze large volume of data in real time, identify patterns, and make informed decisions based on predefined rules and logic. Now, we are arriving to our main contribution of this work, the system framework, that illustrates the architecture of the system and consists of 5 layers. The first one, the physical layer, represents the mining haul track and the material handling systems, including actuators and sensors. The second one, the data acquisition layer, it is responsible for gathering data from the physical layer, and e.g. The mining haul track, and is located within an edge control device known as a PLC. Thirdly, the data management contains a multi-controller data server that enables the synchronization and interconnections of data coming from the data logger systems and controllers in the mine, including the edge control device that supervises our experimental test bed. The fourth layer is the application layer, which encapsulates the industrial supervisory application, the logging and the classification of data, as long as it contains the data processing application that employs algorithms to process the data. Finally, the decision support layer, which provides visualization and analytics, alarms and trends that supports the interpretation of detect anomalies. This layer is crucial in assisting decision-making processes and improving the overall efficiency of the system. So in this scientific paper, we presented a digital twin framework for monitoring mining haul tracks. The proposed framework has 5 layers that provide a cyber-physical system enabling real-time tracking, anomaly detection, and predictive maintenance capabilities. The framework also integrates an expert system that mimics abilities of human agents, providing recommendations to operators and optimizing system performance. The presented digital twin framework is an innovative solution for efficient and effective monitoring and maintenance of complex systems. The integration of machine learning algorithms into the expert system can enhance the framework by breaking the dependency relying on human return on experience and improving its performance over time. As a future work, the development of a comprehensive framework that encompasses all equipment involved in the mining process can be undertaken to create a digital twin of the entire mining process. This can be achieved by incorporating modeling, machine learning algorithms, and co-simulation services to the existing framework to enhance its capabilities and improve the overall performance of the mining process. The digital twin can provide valuable insights into the operation of the mine, optimize the process, and identify areas for improvement, leading to increased productivity and profitability. The development of such a framework and the creation of a digital twin can be a significant contribution to the field of mining and can pave the way for more advanced mining operations in the future. The developed framework was implemented and demonstrated throughout a case study in an experimental open-pit mine, highlighting the benefits of digital twin framework in enhancing the reliability and safety of the monitoring system. Here there are the links of the references used in our work. Thank you for your attention.